This screencast is still kinetics, and it's on activation energy. So all along we've learned that as you increase the temperature, the molecules will go faster, and also the rate will increase because as your molecules go faster, they hit each other quicker and they break down, or they form new reactions. And we're going to use the collision model for explanations. So if you look at the collision model anywhere, it would explain to you basically that molecules collide to react. The more collisions you have, the faster the reaction. If the concentration of molecules increases, meaning there's more particles present, you're going to have more collisions, and you'd have a faster rate. And vice versa. If you have less molecules present, the reaction would go slower because it's less collisions. If the temperature increases, you also have more movement because the molecules are moving faster, they're having more vigorous collisions, and therefore the rate would also increase. Activation energy is the energy needed to make the reaction go. Sometimes you need more energy. You have to go over what we call a hill to make the reaction go. It's kind of like, if you think of it like miniature golf, you have to get up the hill to go to the hole if you were playing miniature golf. Activation energy, though, is going to be a kilojoules value, and it is the minimum energy needed to make the reaction go. Once you achieve that minimum energy, then the reaction will continue on its own. This reaction is not spontaneous. It does not occur on its own, so it needs a specific amount of energy to make it move forward. Some factors that Arrhenius noted whenever he was looking at activation energy is that most reaction rates increase with increasing temperature. So the fraction of molecules possessing the needed activation energy would be higher. There is more collisions per time if the reaction is going faster, and more of the collisions have the appropriate orientation, meaning the molecules are lined up in a way that will allow the reaction to proceed. There was a lot of derivation involved with coming up with the activation energy equation, and some of it's listed here. There's much more in the book. What you need to know is that the R value is 8.314 joules per mole Kelvin. Temperature has to be in Kelvin. And the equation that we are going to use is natural log of K1 over K2 equals activation energy over R times the resulting number of 1 over temperature 2 minus 1 over temperature 1. Some key things: your temperatures have to be in Kelvin, and they're usually not given to you that way. Your R value is most often given in joules. Well, it is given in joules, and your activation energy is often given in kilojoules. So you're going to have to convert one to match the other. So do be careful there. Be careful that you line up the values 1 over 2 and then 2 minus 1 so that you have the matching rate constant and temperature in the correct spots. And then natural log. Now, if you are trying to find the opposite of natural log is e to the x. So if you look on your calculator, the value above the natural log is e to the x. So when you're trying to, like, when we multiply, the opposite is dividing. When you natural log, the opposite is inverse log, which is e to the x.